Hello everyone and welcome to this course on modern application development. Hello everyone. Now we are going to talk about what is an important topic but is not directly related to application development but applies to all kinds of software development in general, which is the topic of testing. So what we are going to look at is what is testing, why do we need it, what are different ways of doing it, and also we will look at some specific aspects that are related to the concepts of the application development as we have been seeing it so far. So we can basically break it down into a set of questions, right? Why, what, when, how, okay? And I'll try and explain why I have put up those titles as we proceed. And finally what I'm going to do is look at one specific way of testing that we have in fact been using as part of this course, and is one of the ways by which you can test Python programs, right? I want to emphasize that it's not the only way of doing it. In general, one of the things you would hopefully have noticed throughout this course is that we are looking more at certain concepts rather than trying to say that this is the particular way of or the only right way of doing something, right? There are multiple ways of attacking any problem. Pytest happens to be one fairly good way of attacking the problem of how to test Python programs, and that's what we'll go into in a little bit more detail. So the first question, why should we test? Okay, and the obvious answer is, what is it that we are testing and does it work as it was intended to? Okay, so does something, right, and I am intentionally leaving this as a vague something, whatever it is. It need not be software, in particular it need not be a web application that we are talking about. But the crucial part is, does it work as intended? Okay, which means that the intention behind the design of this system, whatever it is, must be known, right? And that basically comes from what are usually called the requirements or the specifications of the problem. Okay, so just to give an example, right, it could be something as different from software development as maybe building a car, right? And at the end of the day you still need a set of specifications for a car, right? And in the case of the car, the specifications would probably be, it needs to be able to operate based on petrol, right? It needs to accept petrol as its fuel, it needs to have turn on when certain conditions are met, it needs to be able to travel at a certain speed, it needs to be able to carry a certain number of people, and so on, right? And you would have an appropriate set of tests. As long as if I don't have petrol, will the car operate? No. If I put diesel instead of petrol, will it operate? Well, it might, but probably it will cause problems, right? If I put in more than the adequate load, what will happen to the car? All those are tests that you need to run in order to find out whether the car is testing as intended or is working as intended. Now obviously we are interested in application development, right? Which means that our specifications would be slightly different. It would probably be, what kind of web page gets displayed? How do I decide what goes in which corner of the page? Do I have the appropriate boxes where I can enter data, right? Does it show me the correct page at the correct time for what I want to do? Okay, or not the correct time as such, but under the correct set of circumstances, will it show me the correct page where there is a box where I can enter the data? Or if I need to select some particular thing, like let's say a date, does it show me a date picker, right? Something which allows me to select a date. So all those are parts of the requirements, right? And we need to somehow test whether those are met. Another question that we might ask is, does it respond correctly to inputs, right? So if I enter a date, right, does it actually take the date and store it somewhere? Does it, for example, maybe the date picker was to find out if I am born in a certain year, and does it respond appropriately with whatever is the right kind of message for someone born in that year? Okay, does it respond within a reasonable time? Now this is slightly more non-standard. What I mean by that is, it may not directly relate to the functionality of the system, right? You may be willing to accept a system where you don't really put a limit saying, okay, it has to respond within 100 milliseconds or 1 second. But there might be applications where it actually has to respond within a fixed amount of time, right? One way of looking at it is, you take exams online, right, using a testing software which is running on some computer, and those things have tight deadlines on when they are supposed to start and when they are supposed to finish, right? And they have to, the software itself needs to be tested to make sure that once a person clicks on it, it actually registers the response and then moves on to the next question within a certain amount of time. Because if it doesn't and it's running very slow, that's problematic for the student who's taking the test. Okay. Now all these are sort of the functional specification. After that we come to, can it be installed properly? Does it work in the right environment? Can the environment it needs be set up in a systematic way, right? And finally it comes down to the usability and of course the correctness, right? Is it doing the right thing and is it also usable by the end user? Now this usability and correctness especially are important for software, right? The whole idea of software usability, right? How user friendly is it? Can it be actually used by the right kind of audience, right? All of those are questions that we need to ask. So testing ultimately is asking these questions, right? Are all of them satisfied? In other words, is this something that can be used the way that the original designers intended it to be? Now, what I'm going to do over here is there are a number of different concepts related to testing, and I'm just going to be putting some of them down because these are terms that you need to know or be aware of as we move further into the domain of testing so that you understand some of the concepts that we are talking about. At a very basic level, there are one distinction that you can make between different types of testing is between so-called static and dynamic testing. Okay. Now, what would we mean by static testing, right? What I mean by static testing over here is something like perhaps what's called a code review, right? And in a code review, what we do is we are not actually running the program. We are just looking at the code. There are a bunch of people who are hopefully experienced software engineers, right, or programmers, and who look at the code and sort of look at it without running it and say, okay, this looks all right. Yeah, I mean, the variables seem to be declared okay, the initializations are all right, the structure of the code looks okay, and maybe give suggestions. Look, if you refactor this in some way or write it in a different manner, create a function to take care of this process. All of those things are things that can be done in a code review. The important point and why it is called static is that the code is actually not running at this point. Okay. Similarly, there are certain types of software that can actually do proof checking on other software, right? So if I write a program, I can run it through a so-called equivalence checker or a proof checker, which will be able to prove that this program will actually do what I expect it to do. Now, of course, the question becomes, how do I tell the proof checker what I expected it to do and how does it check that? So there are a lot of intricacies over there, but they can be dealt with, and under certain circumstances at least, they are a very strong way of proving the correctness of something that has been implemented. Okay. Now, on the other hand, the majority of testing that is done is actually a slightly different form. It's called dynamic testing. Okay. And in dynamic testing, what we do is we actually run the program, we check its functionality by applying various kinds of inputs. Okay. I'm saying apply suitable inputs, which means that the suitable inputs might either be the correct inputs that the program expects in order to run, or it might be inputs that are intended to try and break the functioning of the program. Okay, as we'll see later, I mean, there might be circumstances where you want to test for corner cases. What happens if I give the wrong input? The program should not crash, or at least it should crash gracefully, right? It should allow me to recover from the problem. So dynamic testing is the majority of the testing that we are looking at in most cases. Now, while testing a piece of software, there are different sort of levels of detail that we can look at. Okay. At one level, we call what's called white box testing. In a white box, right, and the reason it's called white box is to contrast it with what's the obvious next step, which is the black box, right? And black box, we sort of implicitly understand what it means. A black box is something that you can't see inside. So by the terminology at least, white box means something you can look inside, right? And you know everything about, you have detailed knowledge of how the code is implemented. Okay. Now, the good part about a white box approach to software is that I now know how the code was written. I can look at each and every individual variable, counter, all the different data structures that are there inside the system, maybe put traces on them, right, and watch the values of different variables. And I can also create tests that are based on this knowledge of the internal structure. Okay. Now, the obvious benefit of such an approach is that I have a lot of detailed information about the system, which means that I can usually construct better tests. I will be able to sort of say, okay, look, this is likely to make the system crash. Let me try it out and see how it behaves. Okay, make sure that the system cannot crash under this kind of input. Okay, and if I did not know that it was internally using a certain kind of variable, then I would not have been able to guess something like that. Now, the disadvantage of this approach is that because you know the code, sometimes you tend to focus on parts that are less important. You think that some particular array declaration or something else is the actual problem in the code, whereas if you did not know that it was written using this particular array, you might have said, okay, look, I just need to test functionality and I will focus on just that part alone. Okay. The other problem that happens is it does not encourage the designers to cleanly abstract. And what I mean by that is this, right from the beginning of this course, we have been talking about the separation of concerns, right? The whole idea of HTML versus CSS was that HTML takes care of the semantic markup, CSS takes care of the styling, right? Similarly, in model view controller, the model takes care of the data model, the view takes care of what is displayed to the user, and the controller handles the interaction between the two. All those are examples of separations of concerns. Now, in the same way, when you are designing something, you would like to have a separation of concerns in the sense that the person writing the software versus the person testing the software should ideally have a very clean interface between them. Okay, and the person who is testing should only ideally be able to look at it and say, okay, this is what I expect as the behavior. I really don't want to know what is happening inside. Okay, white box testing, although it makes certain kinds of debugging easier, makes it harder to sort of enforce that kind of a clean abstraction between the two in some cases. Partly it of course depends on the discipline of the team that's doing the development, but you could argue that by enforcing it right to start with, you would have got that benefit all the way from the beginning. So obviously the opposite of white box testing is what we would call black box testing, right? Now in a black box test, only the interfaces are available, right? One way of thinking about this in terms of concepts we have already looked at in the course is that you are only given the API. Okay, you don't know how the API was implemented, but you are given an API and you are given an API specification. You are told that if you make a request to this particular endpoint with this kind of data, then you will get back this kind of a response. Now that's nice because after all the API is something that's going to be made public, right? And I should be able to test at that level, right? The good news from the point of view of the tester is that they are testing something that will actually be seen by the end user, right? The problem is that even if I find an issue, something doesn't behave correctly or something crashes, I may find it harder to actually go in and debug, right? All I can say is something went wrong. I don't have any insight into what actually happened. Okay. The other problem that can happen is I am looking at it only as an API, right? And it's quite possible that I might miss corner cases, certain kinds of inputs that could actually cause the system to crash, right? But which I miss out completely because I don't know how things were implemented internally, right? So let's say for example some counter inside the code, right? Of course this doesn't happen in a language like Python, but let's say if it was C and it was implemented as a 16-bit short integer, okay? I do not know that. As a tester, I just basically test out different values, give different inputs and say that yeah, this works. But a person who actually knew it was implemented as a short might actually try out some set of circumstances which would cause that counter to go beyond 16 bits. And then they would say, yes, that actually triggers a problem. Okay. So there are circumstances where black box testing is not sufficient. It doesn't give you enough insight into what might be going on. On the other hand, the biggest benefit is it is closer to the real world usage scenario, right? And of course, it sort of enforces a clean abstraction. I am only able to give the test engineer the interface. I can't tell them how the code was implemented. Now obviously we would like to also have some kind of hybrids, right, which we call a gray box test, which is a mix of black and white, right? And the idea behind gray box testing is you try and do the black box testing to the extent possible, but the moment you hit a problem, you would want to go into the internal structure, right, because otherwise you can't debug. Now gray box testing requires that the person doing the testing or the team doing the testing has to have the detailed knowledge of the internal structure as well, or at least should be able in close communication with whoever has done that internal implementation. Okay. Now, apart from the box approach to testing, another term which comes up often is this concept of regressions or regression testing, right? And the idea behind a regression is that you have implemented certain functionality in your code and you are continuing to do so, right? And the whole idea of software development is seen as a continuous process, right? It's not just that, okay, I write code, it's done and complete, okay? I have a large design that I need to implement and I go towards it step by step. I implement part of the functionality. Let's say, I'm doing the grade book. I would first be able to create a student, then edit a student, then create a course, edit a course, then finally I would add in the ability to combine the two, right, and assign marks for a student for a given course, right. At each point I want to be able to test and say that, look, now that I'm working on courses, I don't want anything on the student side to break, right. Just because I've added a new table in the database to handle courses, I don't want the student interface to break. Similarly, when I start doing student course marks, right, I don't want the interface or the view for the students to break. Now, each of those would be a test, right? So for example, I might have a test which says that when I want to add a student, it presents me with a certain view, and that view should contain the ability, a button that allows me to add a new user, right, and so on. Now what happens if I change something as a result of, change some internal column in one of the tables in the database, and because of that one of the other views in the student view breaks, right? It doesn't display as it was supposed to. That's called a regression, right? It means that some functionality that was previously working has stopped working. And regression testing is precisely to take care of such scenarios. All it says is anything that has already passed a test, keep track of it, right? And automate it, because it's impossible to run each of these tests by hand for every change that you make to the system, right? But if you can automate it, that's great, because after making every change I can run a regression test suite, right? A test suite is basically a collection of tests. So the regression test suite will go back and make sure that nothing broke as a result of the change that you made now, okay? Sometimes regressions are necessary, meaning that you might actually have to make a breaking change in an API or in a database structure or something else, right? At which point usually the approach that is followed is, if this is production code that other people are already using, you have to inform them. And usually what you would do is you would say, okay, there's a version change. This is why, for example, APIs go from v1 to v2, right, where they say that, look, you can no longer use v1 because there have been some changes introduced that will no longer work in v1, right? You need to switch over to v2. So now how do you handle v1? One possible way is you completely break it. You say that any requests to the v1 API will just result in an error code, which means that whoever had written code using the v1 API will have to go back and fix their code, right? The other possibility is you maintain multiple versions. You say that if you are using v1, yes, I will continue to support it, but you won't have these features, okay? But the point is, a regression test suite allows you to keep track of all of this and tell you what breaks at which point. Now there is another important concept in testing which is called code coverage, right? And basically this refers to how much of the code that you have written is covered by tests, okay? Now what exactly does that mean? What do we mean to say when we say that a certain amount of code is covered by tests, right? What it ultimately, the only thing that you can really say is every line in the code addressed by some test, meaning that will that line get executed as part of some test, okay? And if that is the case, then I can say yes, I have 100% code coverage, okay? Now you have to be very careful with terminology like this, because it is entirely possible to have 100% code coverage, but the code coverage does not really check all possible breaking scenarios for the code, right? In particular, it only means a particular line of code got executed at least once as part of some test, right? But did it get executed for all possible different inputs or different values of the variables that are over there? That's obviously impossible, especially if I have a real numbers or something like that as the input, right? It's not possible to test it for all possible test cases, right? So a code coverage of 100% is not a guarantee that your code is actually bug free. It's not at all a guarantee of that. Okay, all it means is you at least looked at it once. Okay, so please keep that in mind. And in addition to code coverage, which is just line by line coverage, there are a few other forms of coverage which all ultimately have the same problem. They do not guarantee that your code is bug free. All that they can say is, okay, somebody at least looked at it once and some test over there has at least examined this code, so there are no obvious breaking problems with this. There might still be issues under certain circumstances, but it's not that the code is fundamentally flawed or syntactically wrong, at least. So let's take an example. This is an example that is actually treated in Wikipedia, so I'm going to use the same thing because it's a nice compact example that illustrates all the points that we want to make. Okay, and what we have here is there is some function, right? This is a programming language which is basically like C. Okay, and what you can see is that it takes, there is a function that takes in two inputs, x and y. It declares some internal variable. It has some condition check on x and y. Based on that condition check, it updates the value of z and then returns that value. Okay, so if this condition was not satisfied, it should return a 0 and so on. Okay, so I can think of some tests that I could run for this. For example, I might find that I should be able to call this function and say that if the x and y values don't satisfy this condition, then this if condition will not be taken and z should get this value 0, which is what it was initialized to. Okay, so one set of tests that I can create is if x is equal to 0, right, this condition is straight away not satisfied, I should get back z equal to 0. Okay, then I would have some test which basically says x equal to 1, y equal to 1, and at that point I should get back z equal to 1, which is the value of x. Okay, so I can write a few tests saying that foo of 0, 0 should give the value 0, foo of 1, 1 should give the value 1, foo of 1, 0 should give the value 0, because there the y greater than 0 would not be satisfied, and so on. Okay, so those are a set of tests that I can think of. Now in terms of testing, I can also think at different levels. The first is, do I have function coverage, right? In other words, do I have at least one test somewhere in my set of tests which calls this function foo? Okay, now obviously when I have just this one piece of one function over here, the only test I can think of is something that does call this function foo, right? But let's say I'm writing a library of routines, right, where there are like hundreds of different functions that could be called. I need to make sure that every function gets called at least once. Okay, so that's function coverage, right? Then I could go to statement coverage, and over here in statement coverage what I want to check is, okay, I have 1, 2, 3, 4, 5, 6 lines of code inside the function. Okay, is each one of them going to get executed under certain test cases? And the example that we can give over here is if I call it with foo of 1, 1, right, what will happen with x equal to 1, y equal to 1? The first line int z equal to 0, yes, will be executed. The if condition, yes, it will be executed, of course, right, because it's the next statement after that. And then because both these conditions, x greater than 0 and y greater than 0 are satisfied, I will go in here, right. Of course, the open brackets and close brackets are there, but they are not really statements, right. So the next sort of statement is going to be z equal to x. Yes, that will be executed as well. And finally, the return z will also be executed. Okay, so all the four sort of lines of code are going to be executed, and therefore I can say I have 100% statement coverage as far as these tests are concerned, right? With that one test foo of 1, 1, I have 100% statement coverage. Clearly you can see that the fact that I've got 100% statement coverage does not mean I've actually tested the code, because I tested it only for one set of conditions, x equal to 1, y equal to 1, right? I don't know how it will behave under other conditions and whether it will do the right thing. Okay. The next is so-called branch coverage. I have an if condition over here, which means there are two possibilities. One is I take the if, which means I go inside and execute what is there. The second is I do not take the if and jump straight to the return statement. Okay, so I need two conditions, one of which will take the branch, that for example is foo of 1, 1, and the other one which will make me skip over and go to the return straight away. For example, foo of 1, 0 will do that. Okay, so you can see that by having two tests, I can ensure 100% branch coverage. At least all the possible branches over here have been exercised at least once. Okay. And finally, there is something else called condition coverage, right? Now in condition coverage, what we are saying is, look, what were the conditions inside the if statement? There was a x greater than 0 and there was a y greater than 0. What are the possibilities for x greater than 0? Either it is greater than 0 or it is equal to 0, or it is less than or equal to 0. So foo of 0 comma 1 would, for example, test, right? The first condition fails, or rather the first condition fails, the second condition succeeds. Whereas foo of 1 comma 0 would say that the first condition fails and the second, or rather the first condition succeeds and the second condition fails. Okay. Now if you look at those two tests, you will realize that under both these conditions the branch will actually not be taken. For the branch to be taken and to go inside and execute this z equal to x, I need x greater than 0 and y greater than 0 at the same time, which is not satisfied in either of these conditions. Which means that the condition coverage, over here I have 100% condition coverage, in the previous case I have 100% branch coverage, right? But the 100% condition coverage does not guarantee 100% branch coverage, nor vice versa. Okay. So the takeaway from all of this is that 100% coverage of tests should not give you a false sense of security. It should not be taken to mean that my program is bug free, not at all. It only means that it has been looked at under certain circumstances. Those basic tests that you tried passed. Hopefully the tests are good enough to look at all possible problematic cases, but don't sort of assume that just because somebody says, oh, they have 100% code coverage, their program is great and it's bug free. It's not, and that's not a guarantee of anything of that sort. So to summarize everything, right, I mean regarding testing, the requirements for any test ultimately have to be specified by the user. And creating the right kind of tests itself is a huge challenge. It is not at all trivial. One big question that has to be answered is how much knowledge of the code internals should the tester have, right? This is white box versus black box testing, right? And ideally we should be able to separate out the concerns. The tester should only be looking at it as a white box, but at the same time they should also be able to give debug information, which means maybe the gray box is the right approach, but gray box is not clearly enough defined. It doesn't say how much information the tester should have. Okay. So because of all of this, there is always some level of subjectivity in how we go about implementing such tests. And finally, there was this metric called code coverage that we looked at, which is a useful metric because it tells you that at least you have a certain set of tests. It is by no means enough to guarantee that code is bug free. Okay.